Bismillah ar-Rahman ar-Rahim. Last time we were discussing how to design arithmetic circuit that avoids overflow. And the main idea behind these designs is that we check the maximum and the minimum range or limit for the output, and then we extend the bits, the number of bits in the output, and consequently in the inputs to match the output, such that we don't have any overflow. So if you follow the last design example that we discussed, which is this one last time, you should never get an overflow when you perform this operation, okay? When you perform this operation here, 2 times x plus y, where x and y are 4 signed bits, excuse me, you will never get an overflow. And to see that, remember that in order to compute the overflow, what do? We do, well, if Cn XORed with Cn minus 1 is in fact the overflow, okay? Overflow signal, okay? So the overflow function is nothing but Cn XORed with Cn minus 1. So this is C0, which is 0 in this case. Actually, we have 6-bit here, okay? In fact, this is my C6, okay? In fact, this is C1 because we have a carry here that is ignored at this place here, okay? Because of the, the contraction, okay? Design contraction. We are adding Y0 with 0 here, okay? So this is my C0 and this is my C1. C1 is this one here. Okay, C1, C2, C3, C4, and C5 and C6. In this example, you can show that C6 XORed with C5 is indeed always 0. Okay, what does this mean? It means, okay, it means one thing. Who can tell me what does this mean? Who can tell me what this equation mean? Okay, anyone have been studying so far? Anyone have studied the XOR properties?
It means one of them must be 0.
One of them must be 0. If one of them is 0, what should the other be?
Both of them must be 0.
Yeah,
Right?
or
both one. So
yeah, so
they're both
they
the
must
same.
be equal. Yeah, the same. So you can prove this by calculating C5 as a Boolean expression and calculating C6 as a Boolean expression, and then make sure that they are equal. Okay. This is an excellent exercise for you guys. Just try to do it, and you will notice that they are equal. Okay. Go back to the definition of the full adder and find out how you can calculate the carry out as a function of the input. Okay, as well as the sum, of course. The sum is nothing but the XOR of these inputs. Okay. All right, moving on. Now, today we are going to discuss another example, okay, which is the design of a circuit that computes unsigned less than. We have already designed a comparator before, magnitude comparator, okay? But now we are going to use the subtraction to define the comparator operators, okay? For less than, okay, sorry about that. For less than, okay, which is defined to be x less than y, okay, where x and y are unsigned, this is called unsigned less than, okay? We want to calculate x is less than y as a Boolean function, okay, or as a variable, or a Boolean variable. Okay, which means when it is true, this is true, and when it is false, it is false. Okay, so we have, if you move y to the other side, it means that x minus y is going to be less than 0. So if you have a subtraction, if you have a subtractor, okay, and you after doing the subtraction, you examine the sign bit, okay, and you find it to be negative, then your less than will be 1. Otherwise, your less than will be 0. So your less than will be actually the sign bit itself, okay? So what happens is that your less than is going to be the sign of x minus y. So before we have done this x minus y for unsigned numbers, I believe, yeah, this is it's this example where we do the subtraction for unsigned, okay, and we found that you need 5-bit, okay, and we did the analysis here, okay, and we made sure that we contracted the result to the least amount of hardware. So this last full adder is using the properties of the XOR, is nothing but an inverter. So S4 is going to be the inversion of C4. Okay. All right. So coming back here, this is the design with the contracted S4. Okay, and this is my, in fact, my less than, okay, because it is my sign bit. All right. Now for equality, all you need to check is that the difference is, in fact, 0. Okay, if the difference is 0, then the equality will hold. All right. So equality will be defined, okay, to be 1, okay, if and only if S3, S2, S1, S0 is all zeros, okay, else it is 0. All right. Okay. So we don't consider the sign bit for the equality because if the result is equal, okay, then it will be these bits will be 0. Okay, if the result is not equal, then these bits will not be 0. Okay, so the way to check that is to have a K-map. Okay, this doesn't require really a K-map because it's just one min term that is there. Okay, this min term is all zeros, so it is basically S3 complement ended with S2 complement ended with S1 complement ended with S0 complement. So and by De Morgan's law, this is nothing but the NOR of these gates. So if you connect your circuit like this, and take the S's like this. So this is your EQ signal. Okay, this will be your equality signal. All right, and for greater than, for example, okay, you can also create it from. Who can tell me how to create a greater than? It's basically if the sign bit is
positive.
The sign bit is positive and the result is
We
not.
have to specify x bigger than y or y bigger than x.
Yeah, I mean, if we are doing x minus y, okay, x minus y. So how to decide whether x is greater than y or not? First of all, you need to have the sign bit as 0. Okay, so this is it's C4 basically, not without a complement. Okay, and also it has to be not equal as well. Okay, so it's not only that, but it's not equal as well. Okay, so this is your less than. Okay, I mean greater than. All right. Any question? Okay, so if no questions are there, let's move on to another example. So here we are trying to, from what we learned so far, okay, we are trying to calculate or to design a circuit that computes the absolute difference of X and Y, between X and Y, okay, where X and Y are 4-bit signed numbers, okay, in 2's complement representation. Okay, so we do this in 2 steps. Okay, the first step is to calculate W, which is the difference between X and Y. Okay, and we have done this already. Okay, so W here is this example. Where is it? This example. Actually, we haven't done it. We haven't done it for signed numbers, but fine, we can do it. So the range of W is going to be, the maximum W is going to be what? +7 minus -8, okay? This is going to maximize your W, which is +15. And the minimum will be -8 minus +7. So it's going to be -15. So -15 to +15 is covered by -16 to +15. Okay, so your W is going to be, your range is going to be, -16 is basically -2 to the 4. And we know that 4 is n plus 1, in -1, okay? N plus 1. No, -1. -1. So my n is 5, okay? My n number of bit is 5. All right? So we need 5-bit for W, okay? And after obtaining W, using full adders, for example, okay? After obtaining W, we can compute Z as follows. Okay, let me just add another page, another sheet here. So who can tell me what is, let me use the same, in mathematics, using mathematics here. Who can tell me what is, how do we define the absolute value of a number?
It's bigger than 0, it's positive W.
Okay, it's W. You mean it's
Yes.
W?
Yes.
If W is greater than 0. Or
yes.
it's positive, right? And
yes.
it is what?
Negative W if W less than 0.
Less than 0, right? So this is negative. Right? 0 can be included in any case, in any one of them, okay? Okay, so we have learned how to do negative, how to multiply a number by a negative number, by -1 in 2's complement, right? If W, now W is how many bits, by the way? It's 5 bits. So how to check if W is positive or negative? We check the sign bit, right? The sign bit, as I told you in the beginning, regardless of the representation, the most significant bit will be the sign bit. And the sign bit here is W4. Okay, W4 is the sign bit. So that my W here is basically composed of how many bits? Okay, so this is 0, 1, 2, 3, 4. Okay, so this is W4, W3, 2, and 1, and 0, right? So this W here will tell me the sign of the number. If it is 0, then the number is positive. If it is 1, then the number is negative. Okay, so if W4 is 0. Okay, and it is, what is this in 2's complement? How did we define it in 2's complement? Anyone remembers? If we want to add a minus b, okay, how do we do it in 2's complement?
A لا واحدة
A ORed with 1.
A
Not
or
all.
with B complement.
Yeah, it is a plus minus b, which is a. Don't say or, okay? It's this is the addition, okay? This is don't mix it up with or, okay? Plus,
Okay.
you said 3
A.
complement. Is that
Plus
it?
1.
Plus
Yes.
1, excellent.
Plus
So minus w is w complement plus 1, right?
Yes.
Okay, so this is if w4 is what? Is 1, right?
Yes.
Okay. So this is my what? By the way, this is my z, right? This is my z because z is x minus y, the absolute value of that, right? Okay, now I need to use the properties of the XOR gate in order to get rid. I don't like the piecewise definition of a function. I would like to have a function that works for all cases. Okay, so I would like to use my XOR properties, XOR gate properties, to define my function now. So what do I do for that? I can use the sign bit to, for example, if the sign bit is 0, then I need w. If the sign bit is 1, then I need the w complement. So you can for consistency, I will be adding a 0 here. Okay, it doesn't change anything, right? Yeah, and then I can change this to, instead of 0 and 1, I can change this to w4, right?
Yes.
Because w4 here is 0 and w4 here is 1, right? Okay, now for w and w complement, how do I do them? How do I calculate them? Using XOR, right? If you remember XOR, if you have a variable like a, for example, and you XOR it with a 0, if you XOR it with a 0, you get what? You get a. And if you XOR it with a 1, you get what? You guys should know this by now. If you XOR it with 1, you get a 1. So you get an a complement. I'm sorry. Okay. So so what is this now? It's going to be my w4, right? So in case w4 is 0, I get w, and in case w4 is 1, I get w complement, as in the definition exactly. So all I need to do is to replicate my w4 to be at the same width as my w. But yeah, w4. So in this case, if my w4 is 0, then this number will be 0, 0, 0, 0. And if my w4 is 1, then this number will be 1, 1, 1, 1. Okay? Because I need to XOR this with the lowest 4-bit of w, which is represented like this, 3 to 0. Okay? W3 to 0, or you can also represent it as using concatenation operator like this, W3 comma W2 comma W1 comma W0. Okay, why didn't I take W4 with them?
Because it's the sign, the number.
Also because I know that the result will fit in 4-bit. Okay, the result will fit in 4-bit because it's the absolute difference. Okay, eventually it's the absolute difference will be will fit in the in 4-bit. Okay, in 4-bit representation. All right, so the difference will be from 0 to 15. So basically you can if you see that the z will range from z, okay, which is the absolute value of w, which is max z will be what? Absolute value of the maximum x, which is 15 in this case. X and y are signed. No, they are signed. Okay, the absolute value of so it's -8. Okay, this is the maximum that x can get in the negative direction. Okay, and then I subtract that from, in order to maximize my number, I need a positive number here. Okay, so I need a +7. Okay, and that is what? +15, right? And my minimum z will be 0 by the definition of the absolute value. So my range is from 0 to 15. So my z will be only 4-bit. Okay, so why bother about the fifth bit for z? Okay, so I'm going to worry about only these bits of z. And if you add w4, okay, to the list and add one here, add one bit here, it wouldn't change the result. Okay, the result will still be valid. Okay. So let me erase this. Any question about this before I erase it? The range of z.
So the answer is always an unsigned bit, byte or bit numbers. Right.
The answer is the absolute value. The answer is always positive. Okay, you just need to make sure that the magnitude fits here in 4-bit. Okay, and it does fit. So it's from 0 to +15. It can be represented in 4-bit. You get that?
Yes.
Okay. But I hope that it is clear how we get the maximum and the minimum. For the minimum, this is trivial because absolute value, okay, has a minimum of 0 always. Okay, and but you need to check whether we can reach that minimum or not. And what? Give me an example of reaching this minimum by having two equal numbers, right? Any two equal numbers will give you a 0. Okay. So yes, we can reach that minimum. Okay? So we need 4-bit for that. So let me erase this now, and then continue from here. Yeah. So in addition to this, I need to add. I forgot this one here, this bit here of information. I need to add. So this is XOR, and this is arithmetic addition. It's not OR. Okay. W4, which is the same bit. Okay, I need to add the same bit so that I create the 2's complement or the number itself. If the number is positive, then W4 will be 0. Okay, so it doesn't change the value. So so this is the circuit basically. We first need to calculate W. Okay, and then take these numbers here. Okay, and XOR them with W. All right, bitwise. Okay, this means, by the way, what does this mean here? It means that I'm going to create a 4-bit number here, which is going to be composed of W4 XORed with W3, comma, W4 XORed with W2, comma, W4 XORed with W1, comma, W4 XORed with W0. You get that? And then you add addition, okay, arithmetic addition, W4. Okay, correct the result. All right, so this is what it means, being bitwise XOR here. Okay. All right, now what do? We need to create, first of all, we create, this is the circuit here shown. All right, we create W like this using full adders. Okay, basically by doing the subtraction like this, x minus y is going to be equal to x plus y complement plus 1. Okay, so we have y complement here. Okay, and 1 here. Okay, so, and we extend, by the way, we extend each one of x and y sign extend them because they are signed. Okay, they're signed. This is the extension here. And then we just cascade the full adders like this. Okay, and then after creating W's, we use an incrementer by W4. Okay, W4 here, maybe 0, maybe 1, depending on the sign of the answer here. Okay, if the sign of this, if the sign of the answer is positive, then you'll add a 0 here, which will just bypass W to Z. If the answer is negative, then you'll create a 2's complement of W. Okay, how does this work? Basically, so this is the bitwise XOR with W4 here. We have W4 XOR with W0, which will be added to W4 using a half adder here now, because we only have two bits to add. And then there is the carry out will be propagated to the next half adder, which will add W1 XORed with W4, okay, with the carry out from the previous stage, and so on and so forth. Do you get that? So this is your final answer. And it will be a positive number, always a positive number, because it's the absolute value. So it's unsigned, basically. Any question? Okay, let's move on to another example, which is basically, now this example, you can think of it as a review of what we covered in probably many concepts that we covered. We would like to design a circuit that adds up 2 BCD digits, okay? So let me remind you of what I mean by BCD digits first, okay? And then talk about the circuit, okay? Okay, so BCD basically, when we say BCD, and that's it without any specification of the weights, we mean BCD 8421, the code that we learned in Unit 1. So the code that we learned in Unit 1 has 9 or 10 valid codes, okay, which range from 0000, and this represents decimal digit 0, okay, and then followed by 0001, and this represents the decimal digit 1, followed by 0010, and this represents digit 2, and so on and so forth until 1000, and this is for 8, okay, and eventually 1001 for digit 9. Do we have more decimal digits? Do we have more decimal digits in our decimal system? Answer is no. Okay, so these are the valid BCD codes. Anything beyond 9, okay, is considered invalid BCD code. Okay, so let's take an example. Okay, if I ask you what is 1 plus 5, what is the answer? 6. You say 6, right? Okay. Now I would like to do the operation in BCD and see whether I get 6 or not. I have 1 plus 5. This is a 0 with a carry of 1, and a 1, and 1, and a 0. Now, is this answer the answer that I expect?
Yes.
So
Yes.
excellent. Yeah. So far, so good. Okay. Okay. What about we want to do, for example, 6 plus 3, not 3, 4. answer is going to be 10. 10 is actually the valid decimal result. Okay, however, it's not a valid decimal digit. All right. Now let's check what happens when we do it in binary. So 1 0 1 1 0. This is 6, and 4 is 1 0 1 0 0. Well, the answer will be what? 0 1 0 1. Right. And this is not a valid digit. Okay, valid BCD digit. Okay. All right. What is the valid BCD digit? It should be a 0. It should be a 0 followed by a 1, right? So the answer should be 2 BCD digits, right? Answer should be 2 BCD digits. Okay. So how do I make this a 0 now? I need to correct it. I need to correct it in order to make it a 0. Okay. I need to add 6 to it. Okay. If I add 6 to it, okay, then why did I say I need to make it a 0? Because I expect a 0 in the ones digit here. Okay. So by adding a 6 to it, okay, I get a 0. 0 with a carry of 1 and a 0 with a carry of 1, and then a 0 with a final carry of 1. Okay, so this is nothing but this digit is for digit 1. Okay, 0 0 0 1, and then 0 0 0 0 as just expected. Okay, all right, here we added 6. Okay, let's take another example. For example, 6 plus or let's say not 6, let's say 7 plus 5. Answer is 12, right? So if you do it in binary, what do you get? 0 1 1 1, and then 0 1 0 1. The answer will be what? 0 with a carry of 1, and 0 with a carry of 1, and then 1 with a carry of 1, and then 1. All right, I got the correct binary output, but not the correct BCD output. The correct BCD output should be what? It should be 0 0 0 1 followed by 0 0 1 0. Okay, so how much do I need to add to 12 in order to make its ones digit a 6? 2. I'm sorry, a 2. So I need to not 4. No. So I need to make this binary number. I need to make it 2. How much do I need to add to it in order to make it 2, and then with a carry of 1, of course?
5.
How do I find out? Okay, I need to find out by basically subtracting 2 from what we call not 2. So my result here, okay, my result here needs to be 0 0 1 0. Okay, so if I move this to the other side, okay, so 0 plus x equals 0 0 1 0. So my x is going to be what? It's going to be what?
1 1 1 0.
Yeah, 1 1 1. X is going to be actually not. I did a mistake here. It should be 1 with a carry of 1, of course. Okay, so the answer here is binary. Okay, so I need this to be 2 and this to be 1, right? So basically what I need to do is to subtract. So just move this to the other side. So I have 1 0 0 1 0 minus 1 1 0 0. So let's do the review the subtraction with borrow in order to do that. 0, and then minus what? 1 1 0 0. Okay, So this is going to be a 0, and this is going to be a 1, and this is going to be a 1 with a power of 1, and this is going to be a 0 with a power of 1, and this is going to be a 0. Okay, so again, it is, you need to add 6 to that. Okay, all right, do you see that? So no matter what your number is, you always need to add 6 in order to correct it. Okay, if your number is invalid. Okay, do you get that now? So whenever your code is invalid, okay, you add 6 to it in order to correct it. Let me summarize. All of this analysis, okay, is to convince you that always, whenever you have what we call an invalid digit, okay, like this one here, for example, 1 0 0 0 plus 0 0 1 1, for example, 8 plus 3 is 11, right? So the answer will be 11 in binary, but it should be in BCD. I want it in BCD. So in order to correct it, I just add 6. If you add 6, it will be 1 0 with a carry of 1, and then 0 with a carry of 1, and then 0 with a carry of 1. Okay, you see that? This is 11 in BCD. Okay, is this clear? So the bottom line here is that in order to generate a carry, okay, in order to generate a carry to the next digit, we must add 6 to the sum to correct the result whenever the sum is greater than or equal to 10 or greater than 9, basically. Okay, whenever the sum here is greater than 9, we must add 6 to the answer in order to correct the result. Okay, and then we can then let me give you a complete example of a BCD addition. Okay, so let's say I want to add 156 plus 385. Okay, so what is this in BCD? Who can tell me? 156 is 0 0 0 1, followed by 0 1 0 1, followed by, isn't it? Yeah, this is in BCD. Yes. And the other number will be 0 0 1 1 1 0 0 0, and then 0
0 1 0 1.
Excellent. You do the first step is you do addition normally, binary, okay, in binary for every digit alone, and then you decide on correction for every digit. Does it need correction or not? Okay, so here we get a 0, I'm sorry, a 1, and then a 1, and then a 0 with a carry of 1, and then a 1. Clearly, this doesn't need any correction, right?
No.
Okay, excellent. I have somebody who's up with me. Okay, so what do we need to do here?
Add 6.
Add 6. Excellent. So this is going to be the correction step. So add 6 to that in order to get the final result. Okay, so this is going to be a 1, and then a 0 with a carry of 1, and then a 0 with a carry of 1, and then a 0 with a carry of 1. You see that? We carry the result to the next, over to the next digit. Okay? And then we do the addition here. So it's, so this is a 0 with a carry of 1, and then a 1, and then a 1, and then a 1, right? Does this need correction or not?
Yes.
It does. Yeah, it does, because it's greater than 9. So 0, and then 0 with a carry of 1, and then 1 with a carry of 1, and then 0 with a carry of 1. Okay? What about this one? 1 with a carry of 1, and then 0 with a carry of 1, and then 1, and then 0. Do we need correction here?
No.
Excellent. So we just put it down as is. Okay, so this is the result. And do we expect this result or not? So this is 11, and then 14, and then what? 5. Is this correct? Does this match?
Yes.
Yes. So this is the way to do BCD addition, or to carry out BCD addition or arithmetic. All right. Now, so what happens here is that we need to find out, first of all, when to add 6 and when not to add 6, right? So we have this number here that is coming out of a binary adder, a simple binary adder, this number here. Okay, we need to test if this number is greater than 9. If it is greater than 9, then we add 6. Okay, if it is less than 9 or equal to 9, we add 0. Okay, so assuming that your number is B3, B2, B1, B0, this is the output of the binary adder. Okay, all right. Then we have this came up here. All right. So which is 1 here. Okay, whenever the number is invalid. Okay, do you see that? Is it clear why we put the ones of the function here? Anyone have doubts about this? Why are we putting the ones here? The review came up now.
Doctor, why we say B3, B2, or with B3, B1?
Come again? Why do we say what?
Why A6? A6, what does it mean?
It's the output of this function. So A6 means add 6. Add 6 or not.
Okay.
Okay?
Okay.
This is the function. So we would like to design a function that tells us whether we add 6 or not. Okay? So does these ones make sense or not? And they came up. And why? Okay, it means that this one means that my number, this one means that this is 8, 9, 10, right? This has been term number 10. So if my B3, B2, B1, B0 is 10, then it's invalid. So this is 1. This is 11, 12, 13, 14, 15. All of them are 1s. The rest of A6 is going to be 0. So add 6 is going to be B3, B2, this group here, ORed with this group here, ORed with the carry of the binary adder as well. Even if your digit is correct, for example here, if you add, for example, 9 plus 9, what is the result? It's going to be 0 with the carry of 1. And then 0 with the carry of 1. Okay? This is a valid BCD digit, right? However, since you have an overflow or carry out, okay, not an overflow, it's a carry out. Since you have a carry out, then you must add 6 as well. Okay, you must add 6 to correct the result, because what is the result? It should be 18. Okay, and this number is in BCD, it's not 18, it's something else. Okay, this is 12 in BCD. Okay, so you must add 6 to it in order to make it 18. Okay, do you see that? Okay, so this is why we also OR this with the carry from the adder. Okay, so how do we design the circuit? So the logic here is that we have the input, our two BCD digits, X and Y. Okay, and my BCD sum will be X plus Y if X plus Y is less than 10, and it is going to be X plus Y plus 6 if my x plus y is greater than 10. What is x plus y is less than 10 and x plus y is greater than 10 or equal to 10? It is my A6, right? This is A6 complement and this is A6. Yeah? So we have x plus y, and for consistency, I'll put plus 0 here. This is if A6 complement, okay, is true. And if A6 is true itself, then we have x plus y plus 6. Okay? Yeah? So what is the difference between the two now, between the two expressions? I want to put them in one expression. You see here, x plus y is the same. So I put it. It's the same, doesn't change. And the zeros in the boundary are the same. So I put them. Okay? These bits here, okay, they are zeros when A6 is 0 and ones when A6 is 1. So I put A6 in place of these bits. Do you see that? So the circuit, quickly, you can implement it using this logic here. You have a BCD or a binary adder or a ripple carry adder, 4-bit ripple carry adder, RCA, and you have A here, which is 4-bit, X, it's called X, inside it's A and B, all right, which is also 4-bit, and this is Y, all right, and then the sum, from the sum, we will create what? We will create my A6, okay, my A6, which is going to be this function here, okay? So I get the sum, which is going to be 4-bit, all right? And then I take it and then input it to a function called A6, all right, to create my carry out, right? My carry out. All right. And then I add this sum. Okay, I add this sum. And this is carry in, okay, carry in, Cn, and C out. Okay, we have a Cn and C out that are ignored there. Okay, actually, no, not ignored. This one will be also a function of this. Okay, because remember that A6 is also a function of C, okay, which is the carry out of the binary adder. Okay, what else? We have another binary adder here for the correction now, which will be what? 4-bit RCA, and for A we get this sum, and for B we get so we get this, okay, 0 and 0. These are the 4 bits of B. Okay, and this is the BCD sum as named here. Okay, note that since you have zeros here and A6, you will have some kind of you don't need a full-blown BCD adder, but rather maybe you'll have contracted design. Okay, contracted design. For example, let me tell you this from a very simple arithmetic idea. If you add 0 or 6 to the number, 0 or 6 to an integer, okay, do you change the least significant bit or not? In both cases you don't. Okay, in both cases you don't, because you're adding an even number. If you add even number to an integer, you will not change the parity of the number, whether it's even or odd. Okay, So basically, my least significant bit of the sum will be the same least significant bit of this output. Okay, so there is some kind of a contraction here. So try your best to design this using full adders rather than 4-bit adders, and see how it shrinks. The design shrinks when you try to minimize it. Okay, and then this carry out here will be propagated to the. So this is excuse me. This is 1 digit of BCD, and then for the next digit, you just propagate this carry out to the next digit. Okay. All right. Let me stop here because I took more than my time. Sorry for that.